Hi, I'm Irvin. Today I'll present one of my favorite derivations for the Poisson distribution. Poisson is relevant for resource allocation and especially oversubscription. It has this very succinct and useful formula, lambda to the k over k factorial times e to the negative lambda. What this means is that if events are independent and occur on average lambda times in a given interval, then this formula gives the probability that the event will occur exactly k times in a particular interval of that length. For example, if you have a call center that on average gets lambda calls per hour, or a server that on average gets lambda network packets per second, and those events are independent, then Poisson gives the likelihood of getting exactly k calls in a given hour or exactly k network packets in a given second. You can then use the cumulative distribution function to provision resources for a sufficient value of k such that the probability of exceeding k is sufficiently minimal so as to fulfill your service's SLA. The Poisson distribution derives elegantly from a simple and intuitive formula, the binomial distribution. In the binomial, we are given n distinct events, each with independent probability p of occurring. The question is, what is the probability of exactly k of the events occurring in any order? For example, here we have 5 parking spaces. Each has probability p of being occupied independently of the others. The probability of only these 3 spots being occupied is p cubed times the probability that the others are not occupied. To get the probability of any 3 spots being occupied, we multiply by 5 choose 3, the number of ways of selecting 3 spots out of the 5. And in general, for the probability of n spots having exactly k of them filled, we get this, the binomial distribution. Next, we want to extend the binomial distribution to cases where the events occur on a continuous interval. For example, network packets which arrive independently at any time within a given time interval, or customers calling into a support center in a given time period. This is analogous to cars appearing independently on a long bridge where the car lengths are negligible, so that the appearance of any car is independent from any other cars. We will pretend that the bridge is made up of many tiny spaces, each of which may hold a zero-length car. By taking n, the number of spaces, to infinity, we make it vanishingly unlikely that a space will have more than one car. Here again we have the binomial distribution formula. The first thing we'll do is to replace the n choose k expression with its formula, which you'll recall from school. We will take the binomial formula, but in the limit as n goes to infinity. As n grows large, each space gets tiny, so the probability p for any single one of the n spaces will then go to 0. So instead of p, we introduce a new variable lambda, which is the average observed number of occurrences across the interval. For example, the average number of network packets per second, or average support calls per hour, or average number of cars on the bridge. Lambda, the observed average, is a readily available statistic for most problems. If you think about it, the events are independent, so lambda is just p times n. Recall that n goes to infinity while p goes to 0, with lambda stabilizing in the limit. P then is lambda divided by n. So we'll replace p with lambda over n. Next, we contemplate the ratio of these two terms from the n choose k formula, n factorial over n minus k factorial. This divides out to k terms starting with n, n minus 1, n minus 2, and so on. We'll be left with k terms all close to n. As n gets large, the difference between the top terms becomes irrelevant, so we can treat it as n multiplied k times, or n to the k. Next, we rewrite this other expression as lambda to the k over n to the k. we now have two occurrences of n to the k on top and bottom, which we can divide out. For this other expression raised to n minus k, we can rewrite it as the expression raised to n divided by the expression raised to k. Considering the denominator, as n goes to infinity, the interior approaches 1, while the exponent is just the constant k. The denominator therefore approaches 1, and we can delete it. We are now left with this interesting expression with interior approaching 1 as n grows large, but being raised to the exponent n. This may remind you of a classic formula for Euler's number E, but it's not exact. Here is that formula for Euler's number E. As x grows large, the interior gets close to 1 while the exponent rises. In the limit, the expression is E. To massage this into the form we want, we define x as n over negative lambda. Note that as n grows large, x will also grow large. In Euler's formula, we replace x with n over negative lambda, and we replace 1 over x with its reciprocal. We now have almost exactly what we need. We just need this exponent to be simply n. So we raise both sides by negative lambda. We've thereby determined that the right side expression equals e to the negative lambda. Substituting back into the former expression, we now have a formula with no n, so we can remove the limit expression. This is the Poisson distribution. It states that for a continuous interval of space or time with random independent events, where lambda is the average number of events, the probability of seeing exactly k events is given by this expression. We'll then be interested in the CDF, or cumulative distribution function, of the Poisson distribution. The CDF will give us the probability that the number of events is less than or equal to k. Using the CDF, we can choose a k that gives sufficiently large probability to cover our service's SLA, and then provision resources to cover that value of k. For example, let's say our service receives independent network requests with an average of 10 network requests per second. We need to provision support for more than 10 because in a given second, we may get more than 10 requests. Using the Poisson formula, with lambda equals 10, we obtain the probability of getting k requests in a given second. Then, applying the cumulative distribution function, we can obtain a value for k that produces a sufficiently high probability, given the SLA of our service, for example, a k value such that the CDF is over 99.9%. By provisioning support for that higher k value, our service will not exceed resources in 99.9% of second intervals, and therefore fulfill the service's SLA.